All right, so we're recording. It's about to turn on the screen. Oh, and there's Tyreek. Okay, good. And Haley. Okay, good. We're getting everybody. Yay. All right. Okay. All right, as I said, we're rolling back to bases just for a little bit because my notes somehow got mixed up and I completely forgot about a really important thing that I wanted to talk about. So we were talking about before, when we were talking about bases, about, you know, the two conditions for bases. Does anyone remember what they are? Can someone tell me? What were the two conditions that for a set of vectors to be a basis for a particular space?
Just like span W is V and
It has to be independent.
Yes, the vectors have to be linearly independent. Exactly. Good. So we saw a situation when we looked at where we had two vectors, two of them, but we're trying to have them see if they'll span R3. Remember that? And we tried, and it didn't work, right? So we could not get them to span, even though those two vectors themselves were linearly independent, right? So that was the case where we had something that were linearly independent but didn't span. Okay, well, let's look at a case where you have, you're trying to span, let's say, R2. So let's go here. We're trying to span R2. Come on, pen. Okay, here we go. So we'll have our space be R2, right? And then we'd like to span, see if we can span. Or actually see if we can form a basis with the following vectors. Let's see, V1 equal 1, 2, V2 equal 1, 0, and V3 equals minus 1, 1. What is your intuition about whether this is going to work as a basis for R2?
I think this could work as a basis.
Okay, so Jackson's good with that, likes it. Anyone else? We have three vectors here. Good, you like it? Okay. All right, so several people kind of like it. Okay, well, let's see. So let's check for linear independence first. Sound good? So let's go for check for independence. Independence. Okay, so we're going to do that first. All right, so we want to look at the equation 0 is equal to, you know, this linear combination sum of I equal 1 to 3 of the CI VIs, right? So if I want to write that out, I'm going to have 0 is equal to, it's going to give me three equations, as you know, C1. First, I'll write down the big equation. So that this thing just means this, shorthand for this. C1 V1 plus C2 V2 plus C3 V3, right? And so you want to show, right? Remember what the deal is for independence, right? What is the deal? We want to make sure, right? For if it's independent, then there are no C's that will solve this except for zeros for the C's, right? That's called the trivial solution. That's the whole, you know, proof for independence, right? Is that if you can solve this with, the only way to solve it is with all C's being 0, then you have independence, right? If that's not the case, you don't have independence. Got it? So this is going to go give us a couple of equations. So let's see, we have 0, and then we're going to have C1 V1. So C1 V1 here for the first component, right, of the 0 vector. Because remember, the 0 vector is 0, 0. So if this is the first component of the 0 vector, we're going to have C1 times 1 plus C2 times 1 plus, or sorry, minus, let me erase that, that's annoying. I wish there's a button on this pen I can just push to erase, but that does not seem to be the case. Minus C3, right, times minus 1 here, that's C3 times minus 1, right? So plus C2 times minus 1, okay. Then the second component of the 0 vector is going to be C1 times 2C1, and then 0 because C2 is got a 0 there, and then plus C3, right? Got it? So this tells me that C3 is equal to 2C1, right? And C2, quickly, is minus 3C1. Now, what's the now? Okay, fine, right? So is that an issue? What does that tell us? What are your thoughts? Is this tell us it's independent? Does it tell us it's not independent? What does it tell us? What do you think?
Wait, why was it negative 3C1?
Oh, maybe I did the math wrong. Let's see. So we put in C3 is minus 2C1 here. So we got a minus 2C1 here, right? So that's minus 1. Yeah, I don't know. Maybe I did the math wrong. Someone correct me. So let's put it in there. Here we go. So C1, we have C1 plus C2, and then we have minus 2C1, right? So that would give us C2 minus C1 plus C2. So C2 equals C1, right? Did I do that right, guys? Yeah.
Yeah.
All right, there we go. Anyway, okay, so look at these two equations and tell me, what does it tell us? Did we just prove it's independent? Did we just prove it's not independent? What happened?
It um
So what is the condition for independence again?
can only the 0 vector can satisfy it.
Only the 0 what?
It can be 0. Set equal to 0.
What can be 0? What has to be 0?
all the C's.
All the
Yes.
C's. And that has to be the only way to get an answer. Is that true here?
No.
No, because I could put C1 equal 2, right?
Right.
And I would solve the equations. Wouldn't I?
Right. Yeah.
Yeah, no problem. Right, this is not independent, even though it looks independent. Okay, turns out that you can't have, the deal is that you have to have the right number of vectors. So we kind of saw that, right? We saw if we had only 2 vectors in R3, no good, right? Did not span. Even though those vectors were actually independent. Now we have 3 vectors in R2, and they turn out not to be independent. Even though they don't look to me like they're not independent, right? When you look at them, it's really not clear. But they are not. And in fact, you can pick any 3, and any 3 vectors in R2 are going to be linearly dependent. Okay? All right. Okay. So that's an interesting thing, and I think if we go back, let me take a look at our hopefully our theorem to remember has. Let me just get it up here because it's always like hard for me to find. Hope you can see it now. Can you see it there and remember? Okay. Okay, let's look down. Linear independence, bases. Okay. Give me a second. Yeah. So there's not really a, well, there is here. So here, if you look at this one here for linear independent, let's say you have a set of Ks of K vectors in Rn. If K is greater than N, the set is linearly dependent. That's what we just saw, right? So N in this case is 2. So we have R2, and we have 3 vectors in R2. Since K is greater than 2, 3 is greater than 2, the set is linearly dependent. So that's what I just said about having all, you know, any 3 vectors in R2 are going to be dependent. So any 4 vectors in R3 will be dependent. Does that make sense? Yeah. So there's something really unique about that number, right? Right. The number of vectors that you have. Okay. So it looks like the number of vectors has something to do with dimension of the space. And in fact, that is the case. So if you have a number, so if you say, I have a basis for space V, whatever that space is, and it consists of n vectors, then the space is n-dimensional. Okay, so think about it this way. So when I say I have a basis, right? If I have n vectors that that may make up the basis. I have n vectors that make up the basis. Those n vectors already have to be linearly independent, right? And they have to span. So I'm already saying that they do. If that's the case, and they have n of them and they form a basis for V, then V, right, the space V, what the V here, V is n-dimensional. So if you know how many basis vectors you have in your space, you know the dimension. Now that probably seems a little trivial, right? Because you're like, well, yeah, so I know I have 3 basis vectors in R3 and 2 basis vectors in R2, so what, big deal, like. But it actually is quite a useful tool. So for example, let's look at the space. Let's make our space, so an example. So let's make our space of all 2 by 2 matrices. Okay, we want to know what is the dimension of this space. Okay, what is the dimension of this space? How would you go about that? Remember, if you can think of some basis vectors and you know how many, you can figure out how many you need, then you can tell what the dimension of the space is, right? So let's think of a basis. Let's think of like, what is a basis for this? All right, well, it's pretty simple because you have to think a little if you have not used to matrices, remember? But remember the basis is a set of vectors, and in fact, vectors in this case are these 2 by 2 matrices, where you can make any 2 by 2 matrices by a linear combination of those vectors, okay? So, so if I look at basis set that looks like this, so I have one of them, looks like this. Then the other one looks like this. Then another one looks like this. And yet another one looks like this. And that's all I need, actually. That is the standard basis. Remember, like our I hat, J hat, K hat, and three, you know, R3, standard basis for 2x2 matrices. Okay. And now we know what the dimension is because there's 4 of these. So the dimension of V, so like V, so V is the space, is equal to 4. Once you know how many basis vectors you have in any bases, right, you know the dimension of the space. So it's really quite useful, and you may not have guessed that the dimension of a 2x2 matrix, I mean, a space of 2x2 matrices is 4, but it is. Make sense? Okay. So any basis set for this space, whatever it may be, has to have 4 vectors in it. Okay, so it goes both ways. All right. So let's let you try. So let's go for another example. Okay. What is the dimension? So let V be the space of all polynomials of dimension n or less. Okay, what is dimension? What is, move this out of the way, hold on, there's something in my way here. Dim B. Okay, that's for you to work on. How's it going out there?
Is it just n?
No.
Well, I don't,
Why do you think it's just n?
because if we were having, because if it's all polynomials of dimension n or less, then it would, and we just need as many vectors to do it, we just do one vector
Okay.
for each of the
Try n equal 2. So write
Then
down the
it-
basis for n equal 2.
it would be 2.
Really?
Yeah, the two vectors
Okay,
would be
tell me
1, 0.
what would they be?
It'd be 1, 0, and then the second vector would be 0, 1.
But you can't make let's say a polynomial x plus x squared out of that. That's right. How do you make x plus x squared of the vectors 0, 1, and 1, 0?
I don't, I don't know.
Right. You got to write down, remember that the vectors, the basis vectors are members of the space that they span. Right?
Okay. So
So like in R2, it would be vectors that look like, 0, 1, 1, 0, or 1, comma 2, or 3, comma 4, right? In the space of polynomials, your basis has got to be a polynomial vector, right? It's got to also be a polynomial. Can't just, be, I don't know, a vector in R2.
so would it be, wait, of dimension 2, I thought that would just be, I thought 2 would just be like x and then 1.
X and then 1.
X plus 1 or something. I thought that's what you mean by,
I think she means like degree of n,
Yeah, degree
like
n.
x to the n.
Right, so like if that means like
okay,
any
so then
polynomial,
x plus 1. I mean n plus 1.
n plus 1, that's right. So what are the basis vectors? Let's say make up the most trivial, basic, basis that you can think of for polynomials. Let's say of degree 2 or less. What would they be? Anybody?
Wouldn't it be like 1x and x squared?
Yeah, 1x and then x squared, absolutely. Yeah, so let's say if we have n equal 2, a trivial basis, right? The standard basis. Standard basis and trivial basis are the same, the easiest base you can think of, right? Is going to be 1x x squared. So that's dimension 3. So what is the dimension for the polynomial of n or less? What is the dimension? What is dim v if now our polynomial spaces can take degree of n or less? What?
N plus 1.
N plus 1. That's right. Just like Jackson said. Yeah. Okay. So now you know the space. The space has, the dimension n plus 1. I'm sorry, you know the dimension, right? By thinking about a basis. Okay, what about let's see, set of all polynomials of any degree. What's the dimension of that space?
Any degree and only that degree?
No, and less. Yeah, any degree. So that means less too, right? Doesn't it? If it says any. Right.
That'd just be infinite.
It would. Yeah. So there's an infinite dimensional space, right? So certainly dimension can be infinite, which means you need infinite number of basis vectors to span it, right? Doesn't it? Yeah. Okay. I think we're done with what I forgot to tell you. Very important stuff that I forgot to tell you. Okay. We're gonna go back to any questions about this stuff? But I hope it's clear that the number of basis vectors gives you the dimension, right?
Hold on 1 second. I'll be right back.
Okay. So I hope that's clear, yeah? All right, so those two things are linked. Okay. Yeah, so I think we left off with me asking you guys about an inner product space candidate that was a weighted inner product. So let me get a new layer. Okay, and I'll remind you of what we did. So we had a candidate for an inner product space. And so remember, the theorem to remember has all the axioms that an inner product space has to obey. And so remember, an inner product space, you have to have both you have to say what vector space you're talking about in the first place. You have to say what vector space, and then you have to define the inner product. Okay.
Okay, I'm really sorry.
So we're gonna use, and we're gonna use Rn. Okay, that's gonna be our space V. So this is our vector space. And this is gonna be just the usual with usual 115 vectors. Except for now they're n-dimensional. Okay, and we're gonna define an inner product as this. We have suppose we have these numbers Wi with I running from 1 to n, and that we're gonna make them real and positive. Okay, and we're gonna call them the weights. Okay, and then our inner product is going to be defined like this. So we define the inner product that we'd like to see. Can this work? Okay, two vectors in V, U, and V, and the inner product is defined as, W1, U1, V1 plus W2, U2, V2 plus ... Wn, U, and Vn, right? And again, these are just vectors in 115 vectors, but they're in Rn. We'd like you to show that this inner product, this inner product candidate, define inner product here, this inner product candidate will work. Meaning it fits all the axioms. So let's go back to our right here. Right, so there's the inner product spaces and all the things that have to work for an inner product are right here. These 4 axioms. Okay. I'll put that back up. I just want to interfere with your. There you go. Okay, so work on that and see if you can figure out, do all these things hold? for this inner product. And if you would like to make things simpler on yourself, you feel free to just use R2, right? In that case, there'd just be two W's, W1 and W2, right? So if you want to just think in R2, go for it. Excuse me. Any luck out there? Has anyone proved any of them yet?
The first two.
First two, good. Okay, great.
Yeah.
Awesome. Sorry, I just have terrible allergies today. I'm going to mute myself so I can cough. Okay, guys. Anyone got the last one?
I don't think it's correct, or I don't think 4 holds.
Okay, let's take a look at it. How about we just switch to R2? Is that good with you guys? We'll just switch
Sure.
to R2. So we need to prove that the dot product with any vector with itself, the inner product will be greater than 0 with it only being 0 when the vector is 0, right? That's what we need to do. So we need to prove number 4, which is u dot u, not v, they're greater than or equal to 0 with u dot u equal to 0 only if u itself equals 0. Okay, 0 vector. Okay. All right. So let's take a look. So let's just go to R2. So go to R2 for your ease. All right. So now let's do u dot u. So we'll have two vectors, same vector over its inner product with itself. And we'll do w1 u1 squared plus w2 u2 squared, right? Can you tell me, do you think that's greater than 0? Can you tell me if it's greater than 0, do you think?
Yes.
Yeah, why?
U squared is always going to be positive, and W1, W2 are positive.
Yeah, by definition, right? Now, can we show that this is only going to be 0 if u itself is 0? Is there any other way to make that 0?
If W is a 0, but that's not allowed.
Yeah, it says real and positive, and so that does not, 0 does not count as a positive number, right?
Yeah.
Yeah, so yes, holds, right? Yes. So Haley, why did you think it didn't?
Because I read it fast.
Mhm. Yeah, and again, you're right. If we had let the W's be 0, then bad, right? But we didn't. Yeah, and they can't be. They're not negative, and they're real, so we don't have any imaginary number issues. Yep. Okay. Good. So it does. It is a perfectly reasonable dot product. But it's not the kind of dot product you're used to in R2, right? Because used to in R2 is, v1 dot u dot v, and the usual, 115 definition of a dot product. But any operation that takes in two vectors and outputs a number, a scalar, any operation that does that and satisfies the 4 axioms can be an inner product. Yeah? So that's, this is a simple example, but absolutely. And in the time we have left, let me see. I want to show you an inner product on a weird space, right? Let's go back to our, space of 2 by 2 matrices. And that's often denoted by M22, by the way. Okay, let's define an inner product. Inner product given by, U, V, someone just came in. I guess someone keeps getting kicked out and comes back in. It's Tyreek or Tariq, okay. All right, so, sorry, let me get this again. So inner product UV, where these are the two matrices, right? As the trace of U transpose V. Okay, this notation is a little confusing for matrices, so why don't we just stick with 2 matrices, let's have 2 matrices, A and B, right? So we'll call them just 2 matrices A and B. Then our A dot B, but now again, A inner product with B is the trace of A transpose time B. And this is matrix multiplication here, right? So how do we calculate this, right? So I know we have very little time. Let's see if we can do a little bit of it. So we have A is equal to, let's just say A1, A3, A2, A4. Just numbers, right? Just some numbers in there. B is B1, B3, B2, B4. I'm just writing them out of order, right? I went down the columns when I defined this. Okay, so first we have to matrix multiply. We have to take the transpose of A. So A transpose, you just flip over the diagonal, like this. Flip these two right over the diagonal. So we get A1, A2, A3, A4. And now we got to multiply that matrix by B, by matrix multiplication. So we have A transpose B is equal to A1, A2, A3, A4. I'm just writing them down now. I'm going to multiply them in a second. B1, B3, B2, B4. Matrix multiplication, row times column. I get A1, B1 plus A2, B2. And then the next thing I get A1, B1, oh, sorry, B3 plus A2, B4. And the next thing I get is A3, B1 plus A4, B2. That's row times column. This row times this column. Now this row times this column. A3, B3 plus A4, B4. And the last thing I have to do is take the trace. Does anyone know what the trace is? Do you remember? What's the trace? Anybody of a matrix?
Sum of the diagonal.
Sum of the diagonals. So these right here, this plus this. So the trace of A transpose B is A1, B1 plus A2, B2 plus A3, B3 plus A4, B4, right? Look familiar? It's kind of like taking all the components and multiplying them together, isn't it? And adding them, kind of like our usual dot product we have in R2 or R3. Okay, and this actually is a dot product. I'm not going to go through it all, but this actually does work as a dot product, as an inner product, fits all the axioms. Okay, so weird, weird space, weird dot product, but you can have an inner product space of all kinds of things. And we'll keep going with that on Wednesday. Okay, guys, don't forget your homework by tonight. There's new homework out, by the way, as well. So check it out. All right, guys. Bye.